Hello everyone, my name is Matheus Medeiros and I am a PhD student from the University of Pisa. Firstly, I would like to thank the organizers for this amazing event in such a difficult time. I would like also thank everyone who is watching my presentation and thank my collaborators who shared the work which I did my presentation. Today I will be talking about the linearized geodesic light cone gauge, which is based on the reference below. So, alright. Firstly, I would like to give you the outline of my presentation. I will start by an introduction of this nonlinear geometry gauge, which is very useful to describe cosmological observables. And then I will show you how to build cosmological perturbation theory on the top of homogeneous and isotropic geometry background. Then among all the possibilities to fix the gauge on this new perturbation theory, I will show you that how to fix the geometry gauge. And with this geometry gauge, we will compute the cosmological observables, in particular the angular distance redshift relation. And finally, I will present the remarks. Alright, so the geometry gauge relies on describing an event on the path light cone of an observer by attributing to it 4 coordinates to this event. So this tau here is the proper time of a co-moving observer. Another coordinate is the path light cone of this observer that is described by this W. And also we have the angles that connect source and observer on this path light cone described by W. Alright, as you can see here on the left, we have the path light cone of this observer with all the coordinates. Alright, so these 4 coordinates give rise to this metric here. And this metric was first introduced on the literature in 2011 by this reference here. And the great features about this gauge is that both time-like and light-like geodesic are solvable. As we can see here, we have the 4 velocity of the co-moving observer and also the 4 momentum of the photon, both here and here, 4 velocity and 4 momentum. And we can use it this allow us to easily compute nonlinear light-based cosmological observables. As we can see here for the redshift, we just multiply the 4 momentum by the 4 velocity, both on the source and on the observer, and we can compute this rate and obtain the redshift. Also, we can use the 4 momentum of the photon to easily solve the Jacobi map and to exactly solve the Jacobi map, and then we can use the Jacobi map to obtain an expression to the nonlinear angular distance as in terms of geometry parameters. Alright, so if you are interested on the geometrical construction, you can find it in this paper here. And if you are interested on the Jacobi map, you can see it in this reference here. Alright, so the general procedure so far consists on compute a nonlinear cosmological observable in terms of the nonlinear geometry gauge. Then you can perform a coordinate transformation for first or second order perturbation theory to obtain your observable. But here we will give the first step to construct a cosmological perturbation theory directly in terms of geometry. This cosmological perturbation theory will be a first order cosmological perturbation theory, but on the future we plan to extend it to the second order. You can find more details on this paper here, and if you are interested, you can also ask us to further information. Alright, so as I told you, now we will build the general perturbations on the top of homogeneous and isotropic geometry backgrounds. Firstly, we write the Friedmann-Lemaître-Hobson-Walker in terms of geometry coordinates. So we obtain this matrix on the left, and we add 10 degrees of freedom on top of it, so we add perturbations on this background. These perturbations can be further decomposed on scalar and pseudo-scalar. Alright, so since we have 10 degrees of freedom, these degrees of freedom are not physical ones, so it transforms under gauge transformations, as we can see here. So under gauge transformations, all of these parameters of the metric transform. So we have several possibilities to fix the gauge. We discussed some of these possibilities on the paper, but here we will focus on the Jossi gauge. So we will show how to fix the Jossi gauge. Firstly we compare the nonlinear Jossi gauge on the left with this perturbated metric here on the right, and we obtain the gauge conditions on the bottom here. So the Jossi gauge conditions are given on the black box here. So for example, we see that we will use this in the future. For example, epsilon here to compute the linearized redshift. Okay, we have also provided the Jossi gauge conditions in terms of the standard perturbations, and we dubbed this gauge as the observational synchronous gauge since it is more adapted to the observation. So we have on the left the conditions, the Jossi gauge conditions in terms of Jossi parameters, and on the right in terms of the standard perturbations that we dubbed as observational synchronous gauge. Alright, so now let us compute the cosmological observables, in particular the angular distance redshift relation. Firstly, we will need the redshift, so we can use the expression for the epsilon that we saw before, and compute the linearized expression for the redshift. So we see here that this is a very simple expression, doesn't have integrated terms, just this parameter n that is evaluated both on observer and on the source. And now we will give you a general prescription for compute gauge invariant Jossi observables. You can find more details about this prescription on the paper. Here I will try to be a little fast. So this cosmological we still have some freedom on how to parameterize our coordinates, for example, on the source. For example, for the timing parameter, one suitable way to fix the time, to compute the time at the source, is by using the redshift, that is a parameter that we have at hand. So we can define this time in terms of the redshift here. So we define this time here in terms of the redshift, and then we will linearize the any observable that we are interested on. For example, here we give a general example on the bottom. You linearize it, and then you express it in terms of the observed of this time here that is with respect to the redshift. So we will repeat this procedure for the angular distance. So first we linearize it, and then we express it in terms of the observed redshift. So we have this expression for the angular distance. We have this expression for the angular distance, and we already can draw some conclusions about it. The first thing that we note is that it has a very simple expression, and we also note the absence of the integrated terms. Therefore, we see that it preserves the properties of the nonlinear Jossi gauge. And secondly, in the paper, we have also showed that this expression is indeed gauge invariant as expected. We have also obtained an expression for the angular distance in terms of Jossi perturbations without fixing the Jossi gauge, and we see that there are some integrated terms, and we conclude that indeed the absence of those terms is a property of Jossi gauge. So if we perform a coordinate transformations, we can investigate the physical interpretation of these terms. We see here that we have the integrated and the local Sachs-Wolf effect, the time delay, the peculiar velocity, and the latency effects. And uh, all those terms will vanish both on observational synchronous gauge and also on the linearized geodesy gauge. So we see that indeed this gauge preserves the geodesy gauge conditions. All right, so let me draw the conclusions. And here we have developed a cosmological perturbation theory directly in terms of geodesy parameters. And once this geodesy gauge is fixed, the properties of the nonlinear geodesy gauge is preserved on its linearized version. We have also introduced this gauge in terms of the standard perturbations, and it follows the same properties of the geodesy gauge. So this is all. I hope you have enjoyed this presentation, and if you have any questions, feel free to contact me. Thank you. Bye.